All right, so starting with our second podcast, we're going to first of all review the basic types of chemical reactions. We should know some of them, but just in case we don't remember them. First of all, combination. Does anybody remember what else we can call combination reactions? Synthesis, and there's actually another name. Does anybody remember what else we can call it? There's combination, synthesis, and sometimes you might see it as composition. Okay, that's the third type. I don't think I use that very often. But an example of one of combination is if you take magnesium and oxygen and you form magnesium oxide. Now remember that oxygen is a diatomic molecule, so we have to put O2, but then if you look over at our compound, we don't have O2 over there, so then we have to go through and we have to add coefficients to make sure that our charge is balanced, but our equation is also balanced. All right, the second type of reaction is a decomposition reaction. If you guys remember, this means breakdown. So we're breaking one thing down into two different other things. And there's one thing that I'm actually going to show you that you probably we haven't done this before. Calcium carbonate breaks down into calcium oxide and carbon dioxide. Now I am going to expect you this time around to actually understand how this happens. Before, in chemistry, calcium carbonate, you're all like, how does this break apart? I'm not really sure. Does it break into calcium and carbonate? No, it doesn't. Okay, when you see these types of reactions, and it's not just for carbonate, you can also do it for sulfate, so on and so forth. But basically what's going to happen is you are going to break down into two things. You're going to break down into your metal oxide, and you're going to break down into CO2. So when I say metal oxide, well, the metal in this compound is calcium. Metal oxide, calcium plus one oxygen. Whatever you have left, in this case, happens to be CO2. So that's the basic structure of this type of decomposition. So let's do another one. So for instance, let's say I have calcium sulfate instead. I have calcium sulfate, and that's going to break apart. So calcium is 2 plus, sulfate is 2 minus, so that's neutral. So if we're using the same basic concept of how it's going to break apart, what do you think it's going to break apart as? CaO, because there's my metal oxide. Is that neutral? Are my charges balanced? Yeah. Yes. And then what's going to be left out? If I take an oxygen away from sulfate, what's going to be left? Sulfite. Sulfite. So then you're right. Well, see, it's not hard. It's just an extra rule, right? All right, so our next one is single replacement. Okay, so single replacement, an example of this would be if we take potassium and we mix it with water, we're going to get a single replacement, which means our potassium is going to try to replace who? Our hydrogen. Why is potassium going to try to replace hydrogen? Not because, yes, because it's listed first, but because they're both the cations, right? Cations replace cations, anions replace anions. If you guys remember from chemistry, another way to write water is to separate it like this. That allows you to see that we have our cation of hydrogen and our anion of hydroxide. Okay, whenever you see water, especially when you're doing replacement reactions, it might be helpful to rewrite it like this, and then it makes it really easy to see that potassium is going to replace hydrogen, so on and so forth. So that is what a single replacement reaction is. Okay, next is a double replacement. Same basic concept. Our cations are going to replace our cations, our anions are going to replace our anions. So if we look at this example, we have K2CO3 trying to replace BaCl2. So who's going to try to replace who? Potassium is going to replace barium. But if you look over here at our products, you see how I didn't necessarily automatically carry over my K2? Okay, why didn't I carry over K2? Why did I just carry a K? Carbonate has a -2 charge, so in order to make potassium carbonate on our reactant side neutral, we needed 2 potassiums. But on the product side, chlorine only has a charge of -1, so we would only need 1 potassium to balance that out. So now that our products are neutral, we would have to go through the extra step of balancing them. But it would be pretty easy to balance this one, right? Updates. Okay, so the very, very last one we're going to talk about is a combustion reaction. And if you remember, when we're dealing with combustion reactions, we are looking for some things that are combining, usually a carbon compound of some sort, is going to combine with oxygen, release lots and lots of energy, along with what? Water. Water and carbon dioxide. So let's look at an example. So here we have CH4. Again, that's a carbon compound, correct? CH4 is reacting with oxygen, and it is producing CO2 and H2O. Is this a complete or incomplete combustion reaction? Complete. How do I know that this is complete? What's signaling to me that it's complete? Yes, but more specifically, not an additional, but there is an incomplete produce CO, carbon monoxide. Complete reaction produce CO2, carbon dioxide. So that's one signal to tell you if it's complete or incomplete. All right, so there is a quick review over what the basic types are. So now we're going to do a few of these. So first of all, we're talking about normal reactions, non-redox reactions. These are usually include a precipitate, and we're looking for 2 ionic compounds. So these are the ones we did often in chemistry. These are the easier ones to do. So let's do an example. So if we're dealing with cadmium 2 nitrate, okay, it's going to react with sodium sulfide. So first of all, our first step, and before we can balance this equation, before we can write it out, before we can figure out if they can be replacing all of that fun stuff, we have to first of all we need to write out our reactants, we need to write out our products, and we need to write an equation, right? So cadmium 2, what is that 2 telling you? It's charged. So cadmium has a charge of Cd, and it has a charge of +2. Cadmium nitrate, well, nitrate has a charge of -1. So how many nitrates are we going to need? 2 of them. So nitrate is NO3, and we're going to need 2 of them. It is going to react with sodium sulfide. Sodium is what? It's Na, and it has a charge of 1 positive. Sulfide is just sulfur. What kind of charge does sulfur have? 2 negative. So in order to make this neutral, I need Na2S. Okay, it is going to react to form. So first of all, we need to identify what type of reaction is this. So what is this? Double replacement. So cadmium is going to try to replace sodium, and sodium is going to try to replace cadmium. So first of all, we have to figure out, do you think this can happen? So yes, this can happen. If you look at the activity series, you can see that cadmium, which is about halfway down on the list on the page that I asked you to open to 165. Cadmium is right smack dab in the middle. Sodium is above it, so sodium will be able to replace cadmium. Okay, so that's how you read that. You see how sodium is above cadmium? Yes, this replacement can occur. There we go. So we're going to switch them. So we are going to have Na, and sodium is +1, so we only need 1 nitrate. And then we're going to have cadmium, and +2, -2, so both of those are neutral. So then again, you'd have to go through and do a little bit of balancing, but you just add a coefficient right here, and it's balanced. Now, another thing we need to think about is we need to think about if any of these things are soluble in water. Because remember, if things are soluble in water, they are not going to form a precipitate. So we need to see, are there any spectator ions in here? So what do we think? Sodium. Sodium is a spectator ion. And nitrate. These are both spectator ions, correct? So, are we going to get a sodium nitrate product? No. So, this is not going to form because it's soluble. So, this is a spectator ion, and this is a spectator ion. So, if we try to write a simpler formula for this reaction, we can just write that cadmium will react with sulfur. Technically, we should write S8, but I'm not going to just to make things simpler today. Okay? They should react to form yes. No, I just did so that we could remember, because that was given to. Whenever we have transitional metals, I just try to remember to write the charge so I don't forget what it was when I'm trying to do some math with it. All right, so there is one example of a double replacement reaction. Okay, so the next one I want to kind of look at is acids and bases. So we've already kind of talked about naming of them. We're semi-familiar with how to name acids and bases. We're all semi-familiar with what an acid and a base is. So whenever we're doing a reaction, whenever you're trying to write a formula, you need to look for some keywords. So if you see equimolar, which we all remember what molarity is, right? Molarity is how strong the concentration is. So if the concentration is the same, or if we're looking for diprotic, diprotic means that it's an acid dealing with two hydrogens, diprotic. Okay, so some key things here is non-metal oxides in waters will always form acids. So if we have an oxide, so if we have carbon dioxide, that's a non-metal oxide, correct? If you mix it with water, you should be forming an acid. Okay? So let's do an example. Let's do sulfur dye, or we could do trioxide in water. So if I go to try to write out a chemical equation for this, I'm going to write what sulfur dioxide is. What is sulfur dioxide? SO2. So I'm going to write SO2. Okay, to form an acid, we have to mix it with water. So I'm going to write plus H2O. Okay. So then, when I mix sulfur dioxide with my water, I'm going to form an acid of, I bet you guys can already kind of assume how we're going to do this, but how many oxygens do I have right now? 3. How many hydrogens do I have? How many sulfurs? So my acid is going to be H2SO3. There's 3 oxygens, 2 hydrogens, 1 sulfur. Anyone want to take a stab at what acid we are dealing with? What is SO3 first of all? Sulfite. This is going to be sulfurous acid. Okay, so let's do the same thing with sulfur trioxide. What's sulfur trioxide? We're going to do SO3. We're going to mix it with water. And we're going to form, what do you think? H2SO4. So this is sulfate. So the 8 is going to tell us to change it to X, so it's going to be sulfuric acid. Okay? So let's try another example. Let's do carbon dioxide in water. So carbon dioxide, again, is a non-metal oxide, so it's trying to hint to us that we're forming an acid. So if I write carbon dioxide, I'm going to write CO2. It's going to mix with water. And we're going to get a diprotic acid because we have 2 hydrogens. So we're going to write it as H2. And now we have 3 oxygens. CO3 is what polyatomic ion? Carbonate, so this is going to be carbonic acid. All right, so we just said that non-metal oxides form acids. Okay, so if we have metal oxides, we form bases. So what is the difference between a non-metal oxide and a metal oxide? Acids and bases. Non-metal, anything on the right side of the periodic table, right? Metal oxide is like your sodium oxide or your magnesium oxide or any of the metals. So if you see a metal with the first, then you're getting the base. So let's do another example. Let's do solid potassium oxide in water. And I know that I'm going to have to write towards the bottom. I know it's going to be hard for you guys to read that. But we have solid potassium oxide in water. So what is potassium oxide? K2O. Oxygen is a charge of -2. Potassium has a charge of +1. So we would need 2 potassium. I'm going to write K2O. Okay, we're going to mix that with water. And since we have a metal oxide, we know that it's forming a base. So when this reacts, okay, it's going to have to be a combination of some sort. Okay, it's not kind of single replacement, but not exactly, because our end result is not going to have 2 compounds. So that's why I'm calling it a combination. So basically what you're going to do is you're going to, we have K2, we have K2O, and we have H2O, which if you remember, you can write H2O as HOH, so it can kind of help you see what's going to be moving where. But if we have oxygen, so the only other way we can bind something with is if we throw in an H on our K2O. Okay, so what polyatomic ion is yelling at you when you see H2O? We can rewrite it as HOH. What's yelling at you? Hydroxide. So let's pretend we're doing a single replacement. So we're going to have KOH. Hydroxide is -1. K is +1. So we're going to be left with KOH. So then let's think about what's left. We have potassium. We've used hydroxide. So we have left H2 and we kind of have an O, right? So this is where we kind of have to remember how bases work. Bases are we're always going to have hydrogen as one of our products. So this is why I said it's not exactly a double replacement. So we're going to have H2 gas as well on the product side. So this is how bases work. Just like in acids, we know that we're going to have water in the compound. Bases, we have hydroxide in the compound. Okay, acids have hydrogen in the compound. Bases have hydroxide in the compound. So it's not balanced, right? But we could go through and balance it if we wanted to. But does everybody understand how we do acids differently than bases? Okay. And I know that there's writing on the screen. Okay, so now let's do a little bit more complicated reactions. We're going to do redox reactions, which we haven't really talked about what a redox reaction is, but basically we're dealing with reduction and oxidation, so we're dealing with metals and oxygen and how they react with each other. So we're going to use the activity series that I already had you guys open up your book to, and we're going to do a couple of single replacement reactions. So let's do silver nitrate is spilled on a sheet of polished copper. So first of all, we're going to try to convert this into a chemical formula. So silver nitrate. Silver is a transitional metal, but it always has a charge of +1. Silver is always +1. Nitrate is -1. So when I rewrite this, I'm going to rewrite it as Ag. Okay, silver nitrate is spilled on a sheet of polished copper. We all know that at room temperature, copper is in what state? Solid. Okay, so first of all, we have to try to determine, is this reaction going to happen? Because now we have to use the activity series. So what that means is copper going to be strong enough to kick silver out of his spot? So we have to look, is copper above silver on our list? Yes, silver is towards the bottom, almost the very, very last one, and copper is 2 above it. They're both down pretty low, but copper is still technically above. Well, the way I look at it is who's in the compound? Silver's in the compound. So the only way that this reaction is going to happen is if copper can beat him out. So if we had copper nitrate, could silver replace copper? No. So copper would stay in the compound. So the silver replacement, no. Okay, so here we have this. Yes, copper can replace silver, so we're going to rewrite it. Now, the next question you're going to say is, well, which copper are we going to use? We know copper exists as +2 and +3. And the question doesn't say that we're using a specific copper. How I feel about in these types of questions is pick one. It doesn't matter. As long as your equation is balanced and I can tell that you use the +2 version and you're consistent, I'll be happy. So I'm going to use the +2 because it's going to make my math easy. So I'm going to pretend that copper is +2. So when I come over here, I'm going to write as copper, and then we're going to need 2 nitrates this time, because nitrate is -1 to make that nice and even. And then we're going to be left with silver. Okay, so let's try another one. Let's try this one. It says hot chlorine gas is passed over solid iron 3 bromine. This time it told us what our charge of our transitional metal was, correct? So now we need to convert it into words. So as soon as I see chlorine gas, what's popping in your mind? Cl2, it's a diatomic molecule, so I'm going to write it as Cl2, and it told me it was a gas, so I'm going to go ahead and include that. Is passed over solid iron 3 bromide. Iron has a +3, bromine has a -1. So when I write this, I'm going to have to write it as FeBr3. Okay, so next I need to figure out, well, can chlorine replace iron? Well, is chlorine on here? No. So, and is chlorine going to replace iron, or is chlorine going to replace bromine? Bromine, because anions replace anions. So the easy way to do this is look at the periodic table. Chlorine is above bromine on the periodic table, right? So that means chlorine can replace bromine. When you're dealing with non-metals, you just have to look at the periodic table. So if it's above it on the periodic table, it can replace it. So then we go to form our equation. So if chlorine replaces bromine, luckily chlorine and bromine have the same charge, so it makes it easy for us. We're going to get FeCl3 plus, and bromine is another polyatomic ion, so we're still going to have to do, not polyatomic, diatomic. So we're still going to have Br2. I mean, we could go one more step, but I feel like we all know how to balance, so. Okay, so now let's talk about decomposition reactions. So, the first example that I'm going to do is calcium carbonate is heated. How do I represent that something's being heated when I write it in a chemical reaction? Triangle over the yield sign. So what is calcium carbonate? Technical difficulty. Calcium carbonate. Okay, so decomposition, so we have one product. So I already talked about calcium carbonate. I just told you that you have to include a triangle telling me that it has to be heated. We already talked about how calcium carbonate is going to break apart. How is it going to break apart? Into a metal oxide. And then you take whatever you have left, which is going to be CO2. Okay, our next example is going to be sodium sulfate is heated. Same basic concept. We're going to take sodium. Sulfate is SO4. SO4 is -2, so we need 2 sodiums. It is going to decompose by heating, so we're going to put a triangle. How is this going to break apart? Sodium oxide plus sulfite. One oxygen is removed, so then we end with SO3. Yes. Sorry. All right, so now let's look at some synthesis reaction. Usually when we're doing with synthesis reactions, we're looking for one product. Those are the easier ones to do. So if we do an example of our synthesis reaction, remember we're taking two things, we're combining them into one. We have chlorine gas, again, diatomic molecule, so we're going to write it as Cl2, and I'm going to go ahead and include that it's a gas because they gave it to me in the problem. It's passed over iron fillings. Iron usually is in what form at room temperature? Solid. So, did it tell us +3 or +2? It didn't. So what did I say about that? Pick one, be consistent, make sure your compounds match, because honestly, they're going to both exist, so we're going to have both types of equations happening. So, let's pick Fe2+. So, if we have Fe2+, how many chlorines do we need? 2. That's why I picked 2+, because now our equation is nice and balanced. Okay, so the next example is sulfur in its standard state is burned in air. Sulfur, what did we learn about sulfur the other day? It's octatomic, which means that it occurs in 8. So when I go to write sulfur in its standard form, I'm going to write it as S8. So sulfur in its standard state is burned in air. Burned in air. So what do you think it needs? It's going to need oxygen, because we know in order to have fire, we have to have oxygen. It has to be able to breathe. So this is a combination reaction. We only have two things, so it makes it really easy to figure out what our product needs to be. Sulfur and oxygen. Sulfur has a 2 negative. Oxygen has a, that's not going to help us out much, right? So let's think about it. We know that there is SO2. We could do SO2. We also know that SO3 exists. We also know about SO4, but SO4 is probably not going to be our answer because it's a polyatomic ion and those form in different ways. So, like I said before, just like with the 2+ and 3+, it doesn't matter which one of these you pick. Both of them are going to occur. When sulfur is combined with oxygen in the air, you're going to get both of these products. So I don't care which answer you put, both of them are right. So let's do them both. So if it forms SO2, then we have to go through and balance. So we need 8 sulfurs, so we put an 8 here, which gives us 16 oxygen, so we need another 8 there. So that's the right answer. You could also put S8 plus O2 gives you SO3. Put an 8 there to balance out our sulfur, so then we would need 12 oxygen. Both of these are the right answer. I don't care which one you choose. Just make sure that all of your charges balance out. Make sure that your equation is balanced. No, because it doesn't specifically say that heat is being added. Things can burn without heat being added. So unless it specifically says no. All right, so the next one is what I think is going to be the hard one for you. So far today, I feel like everybody's following me along because we're going to come across a new vocab term. Okay, so here we have coordination compounds, or we have complex ion formation. Whenever we are dealing with these, we need to be looking for keywords. So look for something that says like excess concentrated, or if we're dealing with transitional metals, and in this case we're going to include aluminum with the transitional metals, even though it's technically not a transitional metal. In order to do this, we need to take the charge of the metal and we times it by 2, and this is going to give us the Ligand number. New vocab term. What in the world is Ligand? You guys ready? A Ligand is a ion or molecule that is going to bind to a central atom. So an ion or a molecule, so we could be dealing with polyatomic ions. So we're not dealing with elements here. We're not dealing with something all by itself. We're dealing with an ion or a molecule. Usually they are going to donate their electron pairs. So if they're donating their electron pairs, we're probably dealing with somebody bonding with a metal. Okay. So some common ligands that we will deal with are going to be So some common ones that you guys can look for in equations are H2O, Cl minus, OH minus, and NH3, which is ammonia, not ammonium, so it is not a polyatomic ion. This would be an example of a molecule. OH, hydroxide. Okay, so when we do these types of equations, we have to balance the equation by both the mass and its charge. So let's just do an example. Let's make sure that we know what this is. So let's do an example. We're going to take ferric ions and excess concentrated potassium thiocyanate. Excess concentrated, keyword telling you that we're dealing with this type of equation, right? And then ferric. A ferric is actually, there is a different way to name things as opposed to putting the parentheses with a plus charge in it. Ferric is telling you that we're dealing with a +3. I will always give you the Roman numerals. But in this case, ferric is telling us that this is a +3 iron. So ferric iron is an excess concentrated potassium thiocyanate. So right off the bat, I'm going to save us a little bit of trouble. Potassium, is it soluble in water? So that means it's probably going to be a spectator ion. So we're just going to go ahead and cross that guy out. See the spectator ion, let's just not even, he stays soluble in water always, so we're not even going to worry about him. So then we're going to take what's left. We're going to have iron, which is a +3 charge. We're going to have it reacting with thiocyanate, which is written as SC. Okay. This has a charge of -1. So if you look at the rules that I just said, you take the charge of the metal and you times it by 2. So iron has a charge of +3. So what's 3 times 2? 6. So you put the coefficient right here, 6. Okay, this is going to combine to form iron, parenthesis, SCN, and you put that 6 right there. Okay, but is this a neutral compound? No. Iron is +3. We have 6 of these guys, which I told you was a -1 charge. So what's its charge? -6. That is not equal and opposite, right? Does anybody remember how we can denote that? You remember how to do that? Okay, you draw a bracket around the whole compound, and then out to the side of the bracket, which I don't have room, we're going to write that this has a charge of what? -3. So this is coordination compounds. This is just a, this is the one that's going to be a little rough. So Kirsten, what was your question?
What is the iron from?
Ferric ions. Ferric is its Latin name. That's why iron symbol is Fe for ferrous. Okay. So let's do another example, because I'm sure you guys want another example. And so we are going to have zinc nitrate, and I'm actually going to write it up in this blank so you guys can see it a little bit easier. I'm going to write it in the blank above it. So we have zinc nitrate, zinc. Okay, zinc has a charge of 2 plus, and we're going to do the same thing in this example. What do we know about nitrate? It's always soluble. It's a spectator. Let's just go ahead and throw him out. Make our life much easier. So zinc is added to concentrated ammonia. Concentrated, one of those keywords. We also see ammonia, which I told you was a common one that we're going to be mixing with, right? So this is telling us that we're going to be doing this coordination compound process. Ammonia is NH3. It does not have a charge. So what you do, you take the charge of the metal, which is 2 plus, you times it by 2. So what's 2 plus times 2? 4. So then over here, as you rewrite it, you're going to write zinc. You're going to put parenthesis. You're going to do NH3, and we need 4 of them. This has no charge. Zinc has a charge of 2 plus, so this is not neutral, correct? So to denote that, you put brackets around it, and you put 2 plus. This molecule is charged and has a charge at 2 plus. So it's probably going to go on and bond to something else to try to make that charge even out. Okay, so we have a couple of practices underneath that. I'm actually going to have you guys do those on your own just to kind of see if you can, first of all, not understand, but recognize which type of reaction we're happening, know what steps you need to complete. Some of them are just wanting you to balance them, use the matrix system. Some of them give them to you in words, so you have to form these symbols and then come out with them and then balance them. I want you guys to go through the process of balancing them. Some of them you can do technically it's called the inspection model, where you just kind of list the elements and balance them that way. And then lastly, the very last one I'm going to go ahead and tell you is that coordination compound reaction. So number 6, you need to do that step we just did.